We're live. Good morning, afternoon, evening, everyone. We're pleased that you could join us this morning and this afternoon for our second installment of Fike's BESS webinar series. And today we're going to kind of be getting into mitigation techniques, what's available to be able to protect some of those like challenging solutions out there. So I'm really excited to be able to do this today. With me, a couple of housekeeping items before I move on. My name is Carson Stevens. I'm a business development manager for our OEMs and strategic accounts, and I'm super excited to have our general manager of Fike FST, Mark Kendall, on. There he is in the flesh. Morning, Mark. Afternoon. And so let's get into what we're going to talk about today. As I kind of mentioned in the previous slide, before I get to here, here's what we're going to go. We're going to go through our presentation. We've got a video to share at the very end of it, but on the right of your screen, you're going to see in a Q&A area, in the chat area, if you could input some questions as you're coming through. Mark and I are going to try to pick those up at the very end of the webinar, and we'll do our best to answer as many as we can. It's going to probably we'll be short on time, but we'll reach out and we'll make sure that we're answering everybody's questions offline. But in the forum we are here, we'll take care of them as many as we can. So that's the housekeeping things. But what we're going to be talking about today are the BESS quote layers of protection. We're going to use the word layers a lot today, and I think at the end of the presentation, you'll understand why. But the layers of protection we'll be talking about are thermal management, explosion control, early detection, and fire protection. Those are all used kind of, it really depends on the application, but we'll talk about how. And then at the end after we learn what the mitigation techniques are available to us, we'll learn when they should be applied. And at the end of our presentation, we'll talk about a battery hazard analysis and how that can be your roadmap to a mitigation technique that fits your project and not one that's prescriptive, that is all the way across the board, way too many layers or way too few. It's what you'll need for that project. So that's what we're going to talk about today. As kind of just an overview, and I've mentioned this a little bit, is there are multiple layers of protection available to us, to all of us, whenever we're looking to protect a BESS. And why they're so important is that, as I had mentioned, that it's very project specific, and you'll have to know what risk factors are in play for your individual project and what mitigation techniques are available to help with that. So at the end, we're going to be recommending, depending on your project and what it looks like, we'll be recommending a certain form of layers. And like I said, we're going to talk about what these layers are at the end of the presentation, during the presentation. But these layers are important for you because, as I had mentioned, we don't want to overprotect or unprotect a battery energy storage system. It depends on where it's going and how and what risk factors are in play. One of the important things and why we're talking about this today, and I feel like I don't remember when I got this call. It was like 2017 when I got this call of putting some vents on a storage container. And it was that simple at the time, but the technology, the know-how, the industry has developed so much in this day and age that it's really difficult and really subjective to find what you need for your project. And I think what Fike's positioned to do is to be able to be one of the trusted providers, to be able to consult, provide a solution that's what you need and not something that the whole industry is saying that you need. So I think that's a cool thing. So that's kind of what we're going to be talking about today on our BESS protection overview. And I'm going to turn this next part over to Mark as to talk about our first layer of protection, and we'll go through each one of those mitigation techniques. You're muted, Mark. Are you muted? I can't hear you. No,
can you hear?
That's okay.
No.
Oh, you're back. You're back.
Oh, I'm back. Okay, yeah, I'm
Okay.
not muted. Apologies, everybody. I'm currently in France running some tests, funnily enough, on some lithium-ion batteries. So you'll have to excuse me if this drops out a little bit. But the first layer of protection that we're going to take a look at is thermal management. Now, if you were involved, or if you were present for the first webinar last week, where we talked about battery failure modes and how they go into thermal runaway, one of the things that we see initially is that this isn't really a fire problem, it's a thermal management problem. The problem starting in one cell very quickly cascades throughout the battery module and sets the next cell off, the next cell off, and the next cell off. So if we're looking at that, ideally, we want to stop what actually is causing the problem rather than treating the effects. You know, we need to get to the root cause. And the root cause is really that thermal propagation through the battery module. So layer of protection one that we would look at is thermal management. Now, there are a number of ways that you can take care of thermal management or look at thermal management. One is spacing. Air is a fairly good insulator, so having spacing between cells is a method of thermal management. Isolation, having barriers between cells, is another method of thermal management. But what we tend to find, particularly when it comes to ESS applications, is that the energy density requirements of those modules and of those packs precludes you from using those kind of techniques. You can't have spacing because you're restricted and you want to keep energy density. You also need to keep generally something called stack pressure, where there is a certain amount of pressure holding the cells together. So in these applications, we need to do something different. And this is really where we've developed Fike Blue and where we would look to apply Fike Blue. So as we kind of mentioned in the previous webinar, Fike Blue is the first third-party tested solution proven to stop cascading thermal runaway. And the way it works is it's held in a cylinder, and when we detect there's a problem and that there's a battery failing, we inject blue into the battery module itself, and it works by absorbing all the heat and removing all the heat from that battery module as quickly as possible, so that we stop that cascading effect. We don't get the thermal runaway in one cell hitting 3, 4, 5, 6, 7 cells. So we try and limit the effect of that event as quickly as possible. And the way to do that, like I say, is to take care of the thermal management while the thermal runaway is taking place. Now, this is something that's been looked at currently by NFPA 855. So in the 2023 edition, there's nothing in there regarding thermal management systems. However, it is going to come into later editions. So let's say that the internal and third-party testing has proven that thermal management is really the only way to stop cascading thermal runaway. And that you need to cool the battery cells and the module to ensure that you can manage the event, and more importantly, that the cells don't reignite in the future as well, which can happen with some methods that are being employed at the moment. So when we see the new editions or the new versions of NFPA 855, what we're going to see is a section in there that's defined as thermal runaway propagation protection. And that's what we're really talking about with Fike Blue. It's that ability to sink the heat out of the event and stop that event in one cell from cascading through to other cells within the module. So how does it work? Let's say the main feature of Fike Blue is its heat capacity. It has an incredibly high heat capacity above 400 degrees, and that allows it to pull the heat from the event and to then distribute it and take care of it so that it doesn't then overheat the modules adjacent and throughout the pack. It's stored in a cylinder, as we can see on the screen there, under pressure about roughly around 10 bar when it's stored. And then when we detect an event within the module, we push the blue into the piping network. At that stage, it's still held with a heat-sensitive head before it goes into the module. So only when that heat-sensitive head releases does the blue then go into the module itself. The other key feature of Fike Blue is that it's environmentally friendly. It doesn't contain PFAS. It doesn't contain any harmful chemicals for the environment. So it's completely green and can be used without any kind of worry about how that impacts the environment itself. One thing to bear in mind there is, I mean, with things like water is another green fluid or liquid that we could look at using. The volume of water that you need and the runoff is then a consideration when it comes to large-scale ESS applications. You need a lot of water, and as you discharge the water into an event, it will leach the chemicals and everything else that's going on as the thermal runaway is taking place, and it will flow with the water. So you've got to take a look at your environmental conditions and all those kind of things to make sure that runoff doesn't get into the ground, doesn't affect groundwater and all the other kind of bad things that can happen with that. With Fike Blue, because we need a lot less Fike Blue, the same thing will happen. It will still leach the chemicals from the cells as it's going through, but we have much less runoff to deal with, and it's much more manageable to be able to hold that fluid without it getting into the groundwater and affecting the environment around the ESS. So I'm going to hand back over to Carson now for layer of protection number 2.
Yeah. Thanks, Mark. So Mark's kind of gone through the first layer of protection, and as we're going through these layers, you'll kind of put these pieces, connect these dots, and figure out which ones are going to be applicable to me. And that's what one of the takeaways we want. But the next layer of protection would be explosion control, and there are multiple there's multiple ways for explosion control. And what I mean by that is and we're going to go through each one of these, but the idea of explosion control would be to prevent an explosive atmosphere from occurring from an off-gassing event. As I'm sure we've talked about, and you're aware if you're attending this webinar, is for a thermal runaway, for a thermal event in a battery or a module, those release a plethora of gases, and including hydrogen and a few others, but that can get to an explosive atmosphere very quickly in a small container like a BESS. So explosion control is a NFPA 855 requirement, and they use the word explosion control. It's kind of subjective what they mean by explosion control, but the idea is the same. It's you need to be able to manage an explosion risk that's occurring in the BESS. That is the root cause. That the root cause is a thermal event from a module, if that makes sense. So 855, as I mentioned, talks about it being explosion control, but UL 9540A has guidance that says that you have to maintain that off-gassing event 25% of the lower flammability limit. And so that's a very low factor, especially if we're talking about that hydrogen or that hydrogen gaseous mixture that we're talking about. Hydrogen is one of the most explosive fuels in the world. Very dangerous. So back in the day, well, I'll save this for the explosion venting side, but the idea is it's a very, very small volume, but you have to be able to manage that hazard, and you can't let it get to you can't let it get to even close to the LFL. Otherwise, now we're in deep trouble. So the first layer that we're talking about, and Mark's mentioned it a little bit, is Fight Blue. Fight Blue really targets the root cause in that, in the sense that when those cells start to go into a thermal runaway event, Fight Blue enters the module, submerses the cells, the module, in Fight Blue agent, and it will eliminate that thermal event that cascades into cells and cells and cells and modules. And this video that we're showing is a great example of that. This is at our FIKE remote testing facility that we just had a meeting this past week that we're going to quadruple the size of this. So it's going to be even bigger. But the cool part about this video and what you're looking at is that the top part of it is an unmitigated module going into a thermal runaway, which is really cool to see in person. At least for me, I'm a visual learner. I asked to have this. I asked to have this video on my slide, but the thermal runaway you can see is going from cell to cell, and how you know it's going from cell to cell, other than the thousands of thermocouples and temperature gauges that we have on this enclosure at our remote testing facility, but you can visually see it. Nobody's in here. This is a camera. But in the top part, you can see that it's like there's like a small, it is leaking smoke, and then it kind of suppresses just a little bit, but then it'll like resurge with another huge plume of smoke. So each plume of smoke is another cell that's being destructed by that thermal runaway event. So if you can scale this in your head, if you can scale this and say each one of these cells, you can see it blowing off more and more. Each one of them is going into thermal runaway. If this whole module goes off, then it's going to obviously move from module to module. And this is what the setup that we have at the remote testing facility is we're not only monitoring the module's temperature that's going into a thermal runaway that we allow it to, we're monitoring the modules around it to see what Fight Blue can do to mitigate the risk at a module, at a cellular level, and not at what's this going to do to my whole system? We're not looking at that. We're looking at a micro level of what's it doing to the cell. So this is a really cool video that shows. In the bottom part, you can see that when it goes into a thermal runaway event, now there's a little bit of smoke coming out, but that's residual heat that's coming off of the original cell that went into a thermal runaway event. So this is a really cool video. And if you don't take anything else out of this presentation, take this, because this is really cool. But the idea is that for explosion control, you're controlling the explosive risk by mitigating the root cause of what's happening, whether it's overcharge, whether it's overheat, whether it's a malfunctioning HVAC unit in your BESS. Fight Blue can enter the module and suppress the agent and suppress the event from cascading from cell to cell, module to module, and consume the whole enclosure. And this is proof of that. Like I said, I'm a visual guy. This is proof of that. So the first layer of explosion control, if you want to mitigate the root cause, and I'm going to get into this a little bit more, would be to introduce Fight Blue. That would be the number one thing. A method that has been talked about in NFPA 855 a lot is exhaust ventilation. So the idea would be, and because UL 9540A says that it should be the environment should be 25% of LFL, the lower flammability limit. As I mentioned, that's not very much when we're talking about hydrogen in play. So the idea is that each one of these BESS, depending on the manufacturer, depending on your project, will have an integrated HVAC unit inside the enclosure. Each one of them gets it. And so the idea is, hey, we're going to turn on this fan every 60 seconds. We're going to purge it for 10 seconds. It's kind of a rudimentary way to reduce the risk of an explosive atmosphere, but it's an effective one. And it's one that it's easily understood within the industry. So it's an easy one to implement. And it's one that normally a project has at its disposal. So the only downside to this, and we're going to talk about when to apply each layer of protection. The only downside is you can't just put this explosive gas everywhere. If you're in the middle of the ocean, if you're in the middle of a desert, perhaps air permitting isn't required. It's really subjective, but perhaps it's not. I can tell you that where we are at the moment, Mark's in France, but I'm in Phoenix, Arizona at the moment. I can tell you that you're not going to do it in Phoenix, Arizona. I'll tell you that right now. So it's really imperative that you are monitoring what your localized codes are and implementing exhaust ventilation if you're allowed to. But it is an effective form of explosion control. Here's one that I mentioned at the beginning of our webinar. And this is the one that I got this call when I was in explosion protection applications group. I got this call to say, hey, we want to put explosion vents on a storage container. I was like, why? We never do that. It was an emerging market at the time. We've learned so much. Oh my God, we've come so far since then. But the idea for explosion venting would be a more or less a safety net for your solution. So what we've talked about thus far are quote unquote active solutions. So one that either requires some form of detection, some form of fight blue, whatever it is, an agent to be implemented, whatever it is, it's actively working towards mitigating the risk. And explosion venting is kind of the opposite of that. And what I mean by the opposite is it's essentially a piece of stainless steel that's bolted onto your enclosure, like we've kind of shown here, that's set to burst at a predefined burst pressure that's been tested. And if you have an explosion, the doors open. That's essentially what an explosion vent is. It's used in so many applications I don't have time to go through today, but this is another one that's being used for. But think of it as your safety net. And I say this because if you were to implement one of these, it's not proactively preventing an explosion from happening, but it's preventing an explosion from becoming catastrophic. So it's a predefined burst pressure, a relief area on your enclosure that's preventing an explosion from fragmenting the whole BESS. It's opening the explosion vent, allowing the explosion to vent to a safe area. There are some caveats to that. As I kind of alluded to earlier with the exhaust ventilation, you can't put an explosion vent on your enclosure and in the middle of a city and expect it to be applicable or safe for the people around it. We have a lot of applications. We get a lot of calls about these sort of devices going on street corners, going on grocery stores, going in the middle of town by apartment buildings. Like, these are the calls that we're getting. And I don't think the people that are walking out of Walmart are going to appreciate an explosion happening in the parking lot. I don't think they would, but this is a safety net for that. And this is why, and we're talking about these layers of protection that say that if you're going to go put this in an apartment building street corner, what layers of protection are available to me and what's going to be applicable and acceptable for where I'm putting it. The last one is gas detection. So this can work in tandem with the exhaust ventilation idea. And this is a really cool technique that's available because it can sniff the gas, the off-gassing event that's occurring in the BESS and have an early warning detection. Mark's going to get into this in a little bit more detail here in the next couple slides, but this is an early warning detection that if you have an off-gassing event, you can do something about it, whether it is turning on an exhaust ventilation, whether it's initiating a fight blue system and alarming the local fire department. This has that ability to be able to to detect what gaseous atmosphere is typical for your BESS and what's in a non-normal state. If it's non-normal state, it's going to be able to report and do a plethora of outputs that you need for your project. So this is kind of an early warning stage of an early warning layer of protection that it can be used by itself, but also is more advantageous if you're using with other layers of protection so that you can have that solution that works the best for your project. So I'm going to turn it back over to Mark to talk about layer 3 and getting into a little bit more detail of early warning.
Layer 3, we're looking at more traditional types of what we would call fire detection, or what the detection methods that are used within generally the fire industry. Now, again, when we look at a thermal runaway event, we have a number of tells, a number of signals that something's going on. It's an exothermic reaction. So one thing that we can look at is the heat. Now, again, a lot of this depends upon the application and really the makeup of the battery itself as to how these can interact with each other and how you would apply them. But like I say, if we were looking for heat, something like a fiber optic linear heat detection, a digital temperature sensing system could be employed, which uses a fiber optic cable to measure the temperature every half a meter generally. Those can be routed around the batteries or the modules, the container itself, and allow us to build up temperature profiles in real time. The real interesting thing with the fiber optic, there are other types of digital temperature sensing. What we find really interesting with the fiber optics is what we can actually do with that information and how we can interrogate those temperatures, build up profiles over time, ramp profiles to be able to really dial that in to give you a more responsive heat detection type system for an energy storage application. Again, when we look at battery modules, we do a lot with off-gassing. So, when we look at off-gassing, it's kind of a little bit like Carson was just talking about. We're looking for those signatures of the VOCs that are in the gas itself. So things like hydrogen are key. I mean, CO you see used quite a bit. So you're picking up on the gases that are generating as the thermal runaway takes place. I mentioned a bit about separator layer breakdown in the previous webinar. As that separator layer starts to break down and the chemicals start to mix with each other, we get gases produced that we can dial into it and pick up there. Now, one of the interesting things is if you have a sealed battery pack, the likes that we see from second use automotive and things like this, actually the off-gassing stays within the module itself, and it doesn't release particularly well until the event is very much in process and you've got some significant cascading. So that's where looking at heat can come into play along with the gas in some cases, or you may want to look at heat detection rather than gas detection, even though the gas detection can seem like it would be the faster to respond. It is very application specific, and understanding the modules and the application and what technologies are out there. It's really where I feel that FIKE especially comes into its own, because we're not stuck on one of these things. We have all of these things in the toolbox, and we're really able to look at the applications, do the science, and work out what is the most relevant technology to that application itself. Again, smoke detection. You can use standard type point type detection, smoke detection. Again, you're going to need nearly visible smoke before that starts to trigger. We can go up a level into aspirating type smoke detection that is really more sensitive. So it's drawing the air in and then using a laser to interrogate that airflow and see whether there's really small particles of smoke coming through that. You can also combine types of detection. So if we look at an aspirator, we could use an aspirator with a hydrogen sensor on the exhaust, so that we're looking for that visible smoke, but then we're passing it over the hydrogen sensor to also see if we're pulling through any hydrogen in the atmosphere. Hydrogen is quite a good gas to look for because it's not naturally abundant. You don't find it, whereas some of the other VOCs you do find naturally occurring in atmosphere. So again, looking at the application and looking at what's available to us when it comes to detection is really critical for energy storage solutions. One question that we get quite a lot is around the monitoring from the BMS. So the battery management system obviously contains temperature sensors and does an amount of that internally within the battery. A couple of things there, that the temperature sensing and the way those systems are set up really aren't designed for what we want to look for when we're trying to pull information out about an early event, that they're designed for charge monitoring and things like that. So although we can get information out of them, it may not be as reliable or as accurate as we would like when we're looking at a safety system. NFPA 855 at the moment currently says that you need something else there as well as the BMS. The BMS should be combined with another type of detection for this reason. When we look at traditional fire suppression or fire safety systems, we always include redundancy as well. So the BMS alone, like I say, it doesn't generally have these redundancy checks in them. It doesn't include the right kind of monitoring that we look for. Although it is a great additional kind of input into the system to give us as much information as we can. Sometimes it can pick up earlier signs, but it's all about that reliability and redundancy and making sure the system is 100% safe. Layer of protection 4. I just want to jump back a second into the detection, because there's something that isn't kind of covered in here but is within NFPA 855, which is also looking at detection of causes of thermal runaway. And when I say causes of thermal runaway, I mean things like environmental monitoring. So water ingress into the BMS as well is something that you could look at within that detection methodology and can be included, because if you can stop the event before it's even started, I mean, that's good as well. So it's worth keeping those things in mind, as well as your traditional kind of after the event types of detection. So moving on to layer of protection 4. Obviously, we're not just worried about the batteries. We also have switch gear, control rooms, in some cases, air conditioning, environmental conditioners. These all also pose a risk of fire. So we have blue that we look at for batteries, but then in some applications, if we're putting these things into built up environments particularly, we may look at traditional types of suppression systems to work alongside the blue. So in that protection of the switchgear and all the control rooms. So while these are pretty ineffective, well, they are ineffective for thermal runaway, they can be a combination use for them in high risk applications.
Good.
So
after you, Mark. I can.
No, I was handing over to you.
Okay. So you kind of learned thus far about our layers of protection that's available to us. So now it's time to talk about when they should be applied to each one. And there's really kind of two, we found from our experience in talking since 2018 about this stuff, is that there's really kind of two typical applications and risk factors in play, and they have to do with their proximity to people. In a nutshell, proximity to people. So the first one, and especially when we got called about this, was what do I do for my BESS, my ESS that's located in a remote area? That's kind of what I was talking about earlier, like the desert, the ocean, wherever. There are a couple different objectives that you want to be able to address that these layers can help with. And I'm going to get into what those layers, and we can talk about each one. But the first one is to protect the first responders. Everybody kind of knows there's been a lot of videos on YouTube and online about that event that happened actually out in Arizona at a sun farm, that a BSS had an explosive atmosphere that was unmitigated. This was a long time ago, before people understood kind of what the risk was. They opened up the door, introduced oxygen into it, had the right mix of fuel and oxygen ignition, and it hurt people at the bottom line. But the idea is we never want to do that ever again. And so that's our number one priority. And that's really what we do at FIKE, is we're here to protect people. So protecting the first responders that are responding to that event. There's a lot of mitigation techniques or ideas that, to quote unquote, let it burn. That might be feasible if you are out in the middle of nowhere, Antarctica, there's nobody around. You can literally let it burn. That is an acceptable idea, but not one that if a first responder shows up to that thing, that they don't know what that hazard is. So the number one thing to consider is protecting a first responder. The other kind of pieces to that is, and the objectives for installing a BESS in a remote area, is to protect the environment around it. That's kind of what I mean by that let it burn technique. Maybe if you're in Antarctica where there's no air permitting, that would be an acceptable one. But if you're going to put it in Bozeman, Montana, out on the plateau, and you're close to more or less close within a few miles of town, you will need to be protecting the environment. It's not something that you can ignore. So what that would mean would be, perhaps you can't do exhaust ventilation. Maybe you could, but maybe that's an opportunity for FIKE Blue to come in and mitigate the root cause. So that's kind of where you're thinking. And I hope that you guys are actively thinking with me, because at the end of this, we're talking about this a lot. This is an evolving technology. We're not finished with this. We are working. Mark's working on it right now. I mean, there's a lot of people working on this solution, and it's ever evolving. This is not one form. And I see some questions on the right, and please keep the questions coming on the right. Please keep them coming. But a lot of them are around project specific. We're going to talk about that here in a second. But getting back to my slide that I'm on, is protecting the environment could be an objective that's required for your remote installation for a BSS. And then at the end is, how much do you want? If I'm the project manager, how much am I trying to save of the BSS? Do I want 4 layers of protection, where it's like, I only want to lose 3 cells in the module, and I want to rebuild the module? Is your solution that expensive? Or, man, Carson, I don't care. Just let that module, if it takes off and burns, great. That's fine. I just don't want it I don't want to be on the news. Is kind of the idea. And that's okay too. But whatever your objective is and where you're installing it, especially in a remote area, these are kind of the things that should be considered when you're looking at those. And then the vice versa of that is it's super related. But if you're going to put this in the Walmart parking lot, that kind of what we're talking about, or if you're going to put this in the apartment building on top, their solar cells, and you want to do off grid, and you want to do some kind of supplemental alternative energy thing, that's a very feasible thing and a very cool thing. Like, I think we're all on board for that, especially with my electric bill that's happening now. But here's kind of the objectives that we're looking to consider. So if you're going to put this by people, the number one thing, it's kind of obvious, is to protect the nearby people. So one of the mitigation techniques that I just discussed perhaps is off the table. For example, let it burn. I promise you that you're not going to be able to let one of these burn in the middle of an apartment, on top of an apartment building. You're not going to be able to you're not going to be able to do that. And then after you protect the nearby people, then you're protecting the first responders. And how this is different than the old one, the one that I just talked about, is in this particular application, a lot of that early warning detection that Mark's been talking about would need to be in play in this idea, because they are going to want to understand what they're showing up to. Because if I'm a firefighter and I'm trying to take this ladder to the top of a 10-story apartment building and this BESS is on fire up there, I'm going to want to know what the hell it is. If I don't know what it is and I'm showing up to it, I'm not going to touch it. And I'm going to evacuate the whole thing. I'm going to evacuate blocks, city blocks. So if you are in charge of this project and it's located by people, making sure that you have an early warning detection, you're notifying the correct authorities to what hazard is imperative. And then obviously, if it's on top of this apartment building, the example I keep talking about is protecting the nearby properties. You do not want to be able to, you want to be able to mitigate that root cause. Perhaps you want to employ all the layers of protection we just talked about on this one. So that way you're not in the middle of New York City at Times Square and people are having to evacuate city blocks and now you're on the Today Show. You know what I mean? So the idea is you kind of need to understand what risk factors are in play for your application, and protecting nearby properties is one of the things that should be considered if you're going to put this by people. So this is kind of the culmination of where we've been kind of going, and it's the battery hazard analysis. We kind of derived the battery hazard analysis from the DHA, which is a dust hazard analysis, which is an NFPA requirement as well. But a battery hazard analysis is just that. It's identifying what risk factors are in play for your project. It's project specific BHA. And we'll take your technology, your project, we'll send it to our FIKE lab. What you see in this picture is our FIKE remote testing facility, and we're in the middle of a BHA at this. You can see Josh Berry in the background. He's pointing at the screen. I don't know. We probably asked him to point at the screen. I don't know why he's pointing. He doesn't need to point. But then also in the foreground is Tom Farrell, which is our Tony Stark. And those two guys, along with their staff at the remote testing facility, perform BHAs for project specifics. And how it's important and why is it helps a project engineer. It helps a company develop a mitigation roadmap. And what I mean by that is it looks at what your technology is. How hot does it burn? How much FIKE blue does it take? What's the temperature of the surrounding modules when one goes in, when a full-blown thermal runaway event happens in your technology, in your battery technology? It looks at each one of those, formulates a game plan for you and says, hey, here's where you want to be in this market. Here's your risk factors in play. Here's the mitigation techniques that FIKE would be able to recommend to you. And here's how you're going to pass UL 9540A. Because one of the things is it feels like for UL 9540A is you may pass it, you may not. And it's not something that you want to be able to gamble with. It is a gamble whenever you go in, whether you're going to pass it or not. It's not a dollar figure that people are willing to gamble with. And we're not in the gambling game. I think if you're on this call, you're aware of the FIKE brand, that we take this stuff seriously. And when we find a need, we're trying to answer the call. And the FIKE battery at BHA is kind of evidence of that. So formulating a game plan to mitigate the risk for your individual project is what this FIKE battery hazard analysis is going to be. I see a lot of questions on the right that are project specific. This is going to be the answer to those questions is, hey, what is my valve? What kind of valving do I need? What kind of hardware do I need? How much FIKE blue do I need? What agent is FIKE blue? All these questions are answered in your FIKE BHA. And we'll talk about how you can execute one here in a second. But that's kind of the genesis and why we're introducing this, or why we're talking about this, and why it's last and most important is because BHA is going to answer every single one of those questions that you have, so that you don't have to try to guess at the end. You're going to have data. You're going to have empirical, real-world testing data in your report that you're going to be able to show your boss and be like, here's what we did with our FIKE BHA. Here's everything that we need. Here's our BOM. Here's how we're going to execute this whole game plan. And the FIKE BHA is going to be able to do that. Okay. That was a lot. There's a lot of content there. We moved so fast. I realize there's going to be a lot of questions, but Mark and I are going to do our best to answer some of them. So I'm going to go over to the right and pick out a couple. The first question I'm getting is a copy going to be available of this presentation? The answer to that is we're not going to send you a PDF of this presentation, but you're going to be able to receive a link on our Fike portal that you can come and visit this whenever you need. You can share it wherever. But I would ask is if you want to have this presentation, if you want to have this discussion, that's what Mark and I are doing. Like, call us, email us, find us on LinkedIn, and we can help with your individual project. It's not just Mark and I. I mean, there's a full team. There's a full team here that's going to be able to support your project. But I think a good first stepping stone would be Mark or I, and you're going to have our contact info and this presentation available. Mark, do you see any spicy ones that you want to answer? What do you think? We can't hear you. It's your.
Can you hear me now? You're still not getting nothing.
Oh, keep talking. It's coming back.
Okay, yeah.
Yeah, you're back. You're back.
Okay, cool. I mean,
talk loud. Sorry.
There were a couple from David that sprung out to me. So one is around, he's thinking about avoiding leakage after discharge that could short out or erroneously damage other modules, and around the heat capacity of Fike Blue and what characteristics make it superior to water. And I want to answer those two at the same time. So the heat capacity of Fike Blue is, I mean, it's 4 times that of water. Ultimately, it's well above what we see with water. And also, one of the other characteristics that make it unique is it's also a lot less conductive. So we've performed numerous tests over and over again. We've not tripped other modules. We've not reignited after the event, which I was working yesterday and using water to do a comparison test, which had a massive shorting effect within the battery itself. So that is one of the key points of Fike Blue. It is a lot less conductive. We don't see the shorting in the other modules that we do with other fluids. There is a question as well around, well, one question regarding, is Fike Blue a clean agent? No, it's not. It's not a chemical agent at all. It's not like Novec or FK5112. It's not like FM200. It's very different in its makeup. There was also a question around how are inert gases effective on batteries. Completely agree with the rest of that comment. They're not. Lithium-ion batteries self-oxidize as they're burning. So you're trying to keep the oxygen down. At the same time, you're increasing the amount of oxygen through the event itself. So it's very difficult to do that with an inert gas, especially, and this is where having a company that understands how different systems work together, because if you have one company designing your explosion vents and you have another company telling you, I mean, even as a secondary system, that you have inert gas, you need to be careful that the discharge of the inert gas doesn't pop the explosion vents. And then you lose the entire safety system together. So those questions are great. And if you want to chat more about that, please feel free to reach out to us and have a conversation.
Can I grab one, Mark? Okay.
Yeah, of course.
So we're getting a couple questions about how a BHA is executed and what do I need to buy something before we do a DH or BHA? The answer is no. The BHA is purely, in a nutshell, is purely project specific consultation on your battery technology and what hazards exist with your battery technology, because you're not going to know. I mean, you're designing it, but you're not going to know how much gas it's going to off-put or what chemical makeup of the gas that you're off-putting, what it is. The Fike Research and Innovation Center, the remote testing facility that I'm talking about, is going to have inline calorimetry to be able to detect what gases are coming off of your battery technology, how much of it is there, and how much, whatever it is required to mitigate the risk. More than likely, it's going to be Fike Blue, because the reason we're talking about Fike Blue today is that we were just like everybody else. We were just like you guys, where it's like, how much water do we put on this? How much inert chemical agent? Can we submerge it? What can we do to mitigate this risk in these lithium ion battery technologies? What can we do to suppress them? And it's not something that we tried a lot of things. We burned a lot of batteries. And what we ended up is we found, the story is crazy. I'm not going to go into the story, but though Tom and a few other people in that picture that you saw found Fike Blue, brought it to market and said, hey, this is actually working. What do we do now? So that's kind of where the stage that we're in. And we also get a lot of the questions over here about what's the delivery method? What's the hardware required? Do I have to buy the hardware? No, this is all part of that conversation. Like in the Fike Blue in the form that it's in now, that's one way to handle it. And that's one that we know, but the market, these applications are growing. We were just at a meeting last night and we were talking about Dreamland, like self-driving airplanes that are battery operated. That's like what we were talking about. And we know that Fike Blue can help in those mitigation techniques because it stops the root cause. But in the form it's in, it may not be in that form. It may be in a mist. It may be in a lot of other forms. So to answer you the question is start with the BHA. Nothing else is required. Talk to us. Let's get a mitigation technique game plan roadmap for your project so that you can pass UL 9540A, that you can be comfortable and safe in this emerging market that has a lot of questions, that you can stand behind that, and you'll have Fike standing behind it too, because that's what Fike does. So the bottom line is start with the Fike, the BHA, and all that delivery method, whether it's valves or whatever, that's worked out in the BHA because we're going to develop a hardware BOM as a part of that report. So I wanted to say that. Mark, are you seeing anything else that's sticking out to you?
Yeah, hopefully you can still hear me.
Yep, we're good.
Cool. There is one from Chris around the discharge of blue, which kind of feeds into what you were just talking about there. And he talks about how do you make sure it releases into the right module? And that's really some of the work I'm down here doing at the moment, is tailoring a system specifically for a customer's requirements where it comes around to that. There are a number of different ways that we can do that. The most simple is how some of the pictures you saw during this presentation, where we just hold the fluid behind a sprinkler head, in effect, a heat sensitive head that sits within each module itself. That can be through bespoke openings or working with openings on the module, and that's really where the BHA comes in, to be able to look at what that looks like and how we can effectively deliver it. But as Chris mentions, it can also be a selector valve. So it could be a very electronic system where we divert the fluid into the particular module. If we look at very, very early warning release, that would be looking at a selector valve type system rather than using a heat sensitive head. So really we can tailor the delivery system to what you're trying to achieve and the limits that you're looking to accept within that application itself.
Okay, I've got one, and then I think we should probably wrap up after this one, unless you want to grab one more, Mark. But I'm going to answer this one, and then you tell me. But one of the questions is kind of on the module construction and who does the construction of the module, who drills holes and things. That's kind of at the battery manufacturer's level. And part of what the Fike BHA will do will say, here's how big of a hole, or maybe it's not a hole, whatever it is for your technology. This is why it's so difficult to kind of talk at the top level. We're trying to give you, in our experience, where we've gone and what experiences that we have in terms of each application, and kind of culminated into what is the most consistent conversation that we're having. And that's kind of how we've developed what we're talking about. But that's a very, how big of a hole and who does it in the module, that's kind of a really project specific one. But at the end of the day, I think the answer that you're looking for is we as a partnership, whenever we're doing a BHA for you or your client or whoever it is, we'll consult on how big of a hole it's required to get Fike Blue in the module. And then we can go from there. If you want us to drill it on site, we could drill it on site. The dudes can do whatever. But go ahead, Mark. You were going to say something.
I was just going to sort of chip in there, because a lot of the times we're actually working with holes that are already in the module from the battery manufacturer that are either currently used for venting of small amounts of overpressure or gas within the module itself. There are a number of battery modules used within ESS that actually have delivery systems built in. When we look at something like the Samsung SDI system, that's great to be able to retrofit Fike Blue onto, and does a really good job there. So what we're not really, in most cases, or what we're seeing in Europe, we're not really getting people to drill holes in batteries, because as a couple of people have pointed out, you run into some warranty liability issues with that. We're working with battery manufacturers, or we're looking at the batteries and figuring out, okay, how do we get blue in there without causing these issues? And that's where the BHA and the consultancy comes in.
Thanks, Mark. You're the man. There's a lot of other questions here that we're not going to have time to get to, but we want to have the convos. We want to have the conversation. So Mark or I and Caroline, we can all reach out to answer each one of these questions, but let's talk a little bit more in depth about your individual project and see what we can do to help, because that's what we're trying to do at the end of the day. So I want to thank everybody for being on this webinar this morning, this afternoon, this evening. Thank you for the questions. Thank you for your attention, and stay tuned to what we got going on, because we're doing this webinar series. I think we're doing another one next week. We got another one next week, so stay tuned with that. We're doing a lot of an additional webinar series this summer on explosion protection. We're doing podcasts, so just stay tuned to Fike in general, because we're trying to help. So that's all we have for the time. We really appreciate your attention, and we'll see you guys next week. Thank you so much.
Thank you, everybody.
Bye.